Welcome to Chapter 5, Thermochemistry. Thermochemistry has to do with energy. Energy is the ability to do work or transfer heat. Work is energy used to cause an object that has mass to move, and heat is energy used to cause the temperature of an object to rise. One type of these types of energy is called potential energy. It's the energy an object possesses by virtue of its position or chemical composition. And the other type is called the energy of motion, or kinetic energy, which is the energy an object possesses by virtue of its motion. And notice the equation for kinetic energy is 1/2 mv squared, where m is mass and v is velocity squared. Ke stands for kinetic energy. The standard international unit of energy is the joule. The joule is equal to a kilogram meter squared per second squared. Lots of times we use 1,000 joules at one time, called a kilojoule. An older non-SI unit that's still used is called a calorie, C-A-L. 1 calorie is equal to 4.184 joules. To be able to define where energy is transferred from and to, we have to use the terms, or we use the terms, system and surroundings. The system includes the molecules or the atoms or the ions that we want to study. Here in this picture, it's these red and white molecules. The surroundings are everything else. They're this container that's shaped like what's called a piston. They're the air that surrounds this thing. They're anything else that is not the molecules or ions that we're interested in. Work is a type of energy that's used to move an object over some distance. Work is equal to force times distance, where W is work and F is the force, and D is the distance over which the force is exerted. In the chemistry, we don't look at work that often, other than the work that's done by chemicals when they expand or contract. Usually the work is called pressure or volume work. Generally in chemistry, we look lots of times at heat energy. Energy can be transferred in the form of heat as it flows from warmer objects to cooler objects. The transferal of energy, as in heat energy be transferred from warm to cool, can also be illustrated in the form of potential to kinetic energy. The potential energy of this ball right here is determined by its position, or its height, on this little wall. When the ball falls, its potential energy is changed to kinetic energy, the energy of motion. And when it hits the ground, its kinetic energy goes to zero, since it's no longer moving. And some of the energy does work on the ball because it squishes the ball. The rest is dissipated as heat energy. So you can see that potential energy was transferred to kinetic, which was transferred to work and also to heat. All four forms of energy were present in this picture. Thermodynamics, or heat, or energy that we're talking about, whether it be heat energy, work energy, or potential or kinetic energy, is governed by what's called the first law of thermodynamics. And this says that energy is neither created nor destroyed. In other words, the total energy of the universe is constant. If the system loses energy, it must be gained by the surroundings, and vice versa. And there are some diagrams right here at the bottom that we'll spend a lot of time talking about. These are called energy diagrams, and the next slide goes into more detail with those. Any substance that we talk about has a certain amount of internal energy. The internal energy of a particular system is the sum of all the kinetic and potential energies of all components of the system, and we call it E. When we have a sample of atoms, molecules, or ions, it has a certain amount of energy. By definition, the change in internal energy is the final energy of the system minus the initial energy of the system. You can see E final minus E initial. When we have a change in internal energy, we can represent it on a diagram like this. Notice the vertical axis on this diagram is the increase in internal energy. Notice here's liquid water, and here's hydrogen and oxygen. And so we could say this is our reactant, and these are our products. And you can see that the internal energy would have to be greater than 0 to go from liquid water to H2 and O2. Therefore, the system would absorb energy from the surroundings to go from liquid water to H2 and O2. And it makes sense that you'd have to put energy into the water to split it up to become its component hydrogen and oxygen atoms. This energy change is called endergonic. Energy would be less than 0, though, if you took hydrogen and combined it with oxygen and shoved it together to make water. We've done this in a number of demonstrations, and perhaps you've attended some of the shows where we've done this, where you take hydrogen and oxygen and combine them in a balloon and then ignite them with a flame. And of course, there's a reaction where water is created and an immense amount of energy is released in the form of light, heat, and sound. These are called exergonic. When energy is exchanged between the system and the surroundings, it exchanges either heat or work. The symbol we use in chemistry for heat is the letter Q, and the symbol we use in using chemistry for work is W. And you can see heat, or Q, greater than 0 means that the system has absorbed some heat. Work greater than 0 means that the surroundings have done some work on the system. And therefore, the change in energy is equal to Q plus W. So, a positive Q means that the system gains heat, and negative means that the system loses heat. Positive W means work is done on the system, and negative W means work is done by the system. And you can see that there's calculations that can determine what delta E is. This equation, Q plus W on the previous slide right here, is the subject of one of your homework problems on either the first or the second day. They give you work, and they give you heat, and they have you add them together to find out the change in energy for a particular system. The exchange of heat between the systems and surroundings is a very important concept in chemistry. When heat is absorbed by the system from the surroundings, the process is called endothermic. When the heat is released by the system to the surroundings, the process is called exothermic. See what's important to know what the system is and what the surroundings are? Remember, just as a quick reminder here, the system are the atoms, molecules, or ions that we're looking at. The surroundings are the beaker, or the flask, or the container that holds it, and the air that surrounds them. Usually we have no way of knowing the internal energy of a system, and finding that value is simply too complex of a problem. And so what we look at is we look at the internal energy of a system before and after a change occurs. We can find, or we do know, that the internal energy of a system is independent of the pathway by which the system achieves that state, whether water goes from 100 degrees Celsius to 25 or from 0 to 25. The heating or cooling process can be measured for its change in internal energy. Even though we might not know the absolute internal energy of one system, we can find the change of both of these processes. Therefore, we say that internal energy is what's called a state function. It depends only on the present state of the system, not on the path by which the system arrived at the state. And so, the change in energy depends on the initial and the final states of the system. However, Q and W are not state functions. Whether this battery in this picture is shorted out, like it would be on a heating coil like this, or it's discharged by running the fan and therefore doing some type of work, the change in energy is the same. But Q and W are different for both of the cases. In the fan, there's some work done because the fan blade actually moves. In the heating coil right here, where it's shorted out, only heat energy is dissipated and no work is done. When a process occurs in an open container, commonly the only work done is a change in volume of the gas pushing on the surroundings or being pushed on by the surroundings. We can measure the work done by the gas if the reaction is done in a vessel that has been fitted with a piston. You can see this device right here is called a piston because it can slide up and down inside of this container. You can see here they've got a small amount of zinc and they're going to put it in some hydrochloric acid, and when you do that you're going to make some hydrogen gas. The hydrogen gas then pushes against the piston and shoves it up. This distance that it moves the piston causes some amount of work. Now, the PowerPoint here spends a good amount of time talking about work and talking about the negative pressure and volume that takes place. But truth be known, most of the things that we do in chemistry don't involve a really large pressure change, because we do them in a beaker or a flask or something that's open to the atmosphere. Lots of the reactions take place at constant pressure. The only work that's done is pressure volume work, and we can account for the heat flow during this process by measuring what's called the enthalpy of the system. Enthalpy is the internal energy plus the product of the pressure volume work. And if there's not a lot of pressure volume work done because we're at a constant pressure, we're in an open container where the atmosphere doesn't change much in pressure, we can say that enthalpy is equal to the energy at constant pressure. And they go through a little derivation of finding this thing called enthalpy, which is symbolized by a triangle H right here. But bottom line, when it's all done, and all of the equations are canceled out, you can see that Q is equal to H. Q, which we called heat earlier, is equal to enthalpy as long as the pressure is constant. And so we use these terms interchangeably lots of times, H and Q. H called enthalpy, which is simply heat energy at constant pressure. A process is endothermic then when delta H is positive, or when enthalpy is positive. A process is exothermic when delta H or enthalpy is negative. The change in enthalpy is the enthalpy of the products minus the enthalpy of the reactants. And you can see here on this enthalpy diagram, heat energy at constant pressure increases as we go from CO2 and H2O to CH4 and O2. Notice we would have to add 890 kilojoules of energy to cause this process to occur. That would be an endothermic process because we'd have to add energy to make that happen. Conversely, when CH4 and O2 combust and form carbon dioxide and water, which happens in hydrocarbon combustion all the time, we would release, and that's why it has a negative sign right here, 890 kilojoules of energy. The quantity, delta H, which is known as the enthalpy of a reaction, is also sometimes called the heat of a reaction. And as we just showed a little while ago, when we take H2 and O2 and combine them together and form water, notice that it is an exothermic process and energy is released. In this picture is actually an exploding hydrogen and oxygen balloon. So what's the truth about this new word called enthalpy? First of all, enthalpy is an extensive property of matter. It depends on how much you have. If you have 1 gallon of gas and burn it, you're going to get a certain amount of energy. If you have 20 gallons of gas and burn it, you will get, of course, 20 times more energy. Enthalpy for a reaction in the forward direction is equal in size but opposite in sign to the enthalpy of the reverse of the reaction. And enthalpy for a reaction depends on the state of the products and the state of the reactants. Whether they're liquids going to solids, or solids going to gases, or gases going to solids, that makes a difference. Well, how do you measure this thing called enthalpy, or this heat energy? One way is through a thing called calorimetry. Since we can't know the exact enthalpy of reactants and products, we measure the change in enthalpy. Remember, this triangle right here means change, and H means enthalpy, through something called calorimetry, the measurement of heat flow. The amount of energy required to raise the temperature of a substance by 1 Kelvin is called its heat capacity. And we define specific heat capacity, or simply specific heat, is the amount of energy required to raise the temperature of 1 gram of substance by 1 Kelvin. Specific heat then is equal to the heat transferred, sometimes known as Q or delta H for a constant pressure, divided by mass times temperature change. And this equation right here is on your periodic table that's given to you on all the tests and quizzes, except it's in a little bit different form. We actually take m times t and bring it over to the other side over here, and it's Q equals m times s times delta t. By carrying out a reaction in an aqueous solution in a simple calorimeter such as this one can indirectly measure the heat change for the system by measuring the heat change for water in the calorimeter. You can see this simple calorimeter is just made up of 2 styrofoam cups that allow heat to remain inside of the calorimeter and not flow anywhere else. And then we can measure the heat change with the thermometer that's in here. Because the specific heat of water is well known, 4.184 joules per mole Kelvin, joules per gram Kelvin, that should be, I think that's a typo, we can measure the enthalpy for the reaction with this equation. Q equals mass times specific heat times the change in temperature, m for mass, s for specific heat, triangle T for change in temperature. Q is the heat of the reaction. Reactions can also be carried on in a sealed bomb calorimeter, such as this one, and measure the heat absorbed by the water. Notice in this container right here, called a bomb calorimeter, there's a cup that holds the sample. Notice it's all surrounded by water, and there's a little stirrer right here. There's an inlet for some oxygen, and then there's some fine wire that comes over here and ignites whatever substance we put in there. Because the volume in the bomb calorimeter is constant, what is measured is really the change in internal energy, delta E and not H. For most reactions, though, the difference is very, very small. And we can say in this case that it is, in most cases, that you can use a bomb calorimeter to find the delta H, even though there is a slight change in pressure. Well, there's another way to find the enthalpy or the heat of a reaction as well. Besides a calorimeter, you can use something called Hess's law. Since the enthalpy is well known for many reactions, and it's inconvenient to measure delta H for every reaction which we're interested in, we can use Hess's law to estimate the enthalpy values using some already known values of enthalpy. Hess's law states that if a reaction is carried out in a series of steps, the enthalpy for the overall reaction will be equal to the sum of the enthalpies for the individual steps. Because enthalpy is a state function, the total enthalpy change depends only on the initial state of the reactants and the final state of the products, not on the pathway for which it took to get there. If we take a look a little bit closer at this enthalpy diagram, we can say, here's the start, here's the end, and the overall enthalpy for this reaction is negative 890. But if we wanted to look at it in a series of steps, we could say, okay, these two things are going to react and form these things. And then these things are going to react and form this stuff. The addition of these two steps has to add up to equal the enthalpy of the overall reaction. That's what Hess's law says, is that two reactions that end up in the same place can be added together, and their enthalpies can be added together to yield the overall enthalpy. Well, there's a third way to find enthalpy as well, and this one's called enthalpies of formation. An enthalpy of formation is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. Standard enthalpies of formation are measured under standard conditions at 25 degrees Celsius and 1 atmosphere of pressure, and you should memorize this. 25 degrees Celsius is called standard temperature, and 1 atmosphere of pressure is called standard pressure. And here are some enthalpies of formation 4 different compounds, meaning that these compounds were formed from their elements at 25 degrees Celsius and 1 atmospheric pressure. They're symbolized by a triangle H with a little F down here, meaning enthalpy of formation, with a little degree sign right up here at the top. This little degree sign right here means standard conditions, 25 degrees Celsius and 1 atmospheric pressure. To calculate the enthalpy, imagine this reaction occurring in 3 steps. First, C3H8, goes to carbon graphite, 4 hydrogens, 5 oxygens. Then the graphite plus the oxygen becomes carbon dioxide. And you can see this one circled over here in pink as well. And then lastly, or thirdly I should say, the hydrogen and the oxygen form H2O. And you can see that when you add all 3 together, you get the overall enthalpy of the reaction. The overall enthalpy of the reaction. You can see each of these reactions up here are written as their enthalpies of formation. Carbon and oxygen, elements in their elemental state, forming carbon dioxide. Hydrogen and oxygens, elements in their elemental state at 25 degrees Celsius, going to form water. And this would actually be the backwards of an enthalpy of formation right here. And anyway, Hess's law says that you can add those 3 together and you'll get the overall enthalpy for the whole reaction. So we can use Hess's law in this way when we do enthalpies of formation. We can say that the summation of the enthalpies of formations of the products minus the summation of the enthalpy of formation of reactants is equal to the overall enthalpy of the reaction, where N and M are both the stoichiometric coefficients from the balanced chemical equation. For example, if we had this reaction with the combustion of propane, we would take the products, water and carbon dioxide, and look up their enthalpies of formation. This is carbon dioxide, and this is water. Notice there's a 4 here because there's a 4 in front of the water, a 3 here because there's a 3 in front of the carbon dioxide, and subtract it from the reactants. The reactant CH3's enthalpy of formation is 103.85, and oxygen's enthalpy of formation is 0, because any substance in its elemental form at 25 degrees Celsius and 1 atmosphere has an enthalpy of formation of 0. Products minus reactants is equal to the overall enthalpy of the reaction. We plug those numbers in and multiply them together, and we end up with an overall enthalpy for the reaction of I guess it doesn't give us the overall enthalpy. It was supposed to be on this slide right here. Maybe it's supposed to come over here. But it's negative 2,323.7 minus 103. So it ends up being about 2,200 something kilojoules for the overall. Negative 2,200 something kilojoules for the overall reaction. Lastly, your textbook has a small section about the energy in foods. Most of the fuel in the food we eat comes from carbohydrates and fats. The vast majority of energy consumed in this country comes from fossil fuels. And they talk about the energy not only in foods, right here is a bunch of carbohydrates, fats, proteins, and it gives you the fuel value, but it also talks about the energy in fuels like coal, petroleum, natural gas, and renewable resources. And you can see the approximate composition and the fuel value of those fuels. Good luck on your Chapter 5 Thermochemistry